So welcome back everyone, this is still DB2 and this is still our discussion of chapter 9 on ordered indexes. But this will not be about B+ trees anymore because we are switching gears and switching over from PostgreSQL to MonetDB. And as you will see, there are indeed special algorithms and special techniques built into MonetDB to support the evaluation of predicates on ordered domains, but they are not tree-based. These techniques are not tree-based. B+ trees don't play any role in MonetDB. So there must be something else there. And this video and I think the next two videos will explore what we do find in MonetDB. Okay. Right, so we are still left with the task of filtering a table. And for that we had already defined a probe query. And well, there it is, the probe query, the filtering a table probe query. You have seen that query before. All right, so we are looking at the indexed table. Well, we will see that we can indeed index a table in MonetDB. And that table had 3 columns. We are currently selecting according to the A values in the A column. Equality test on column A regarding literal 42. Later on we will switch over to a different column, a decimal column or numeric column, and we will have an equality test there too. Okay, so as I told you already, indexes in MonetDB are not organized in tree shapes. And that's for a good reason, because we are operating in a main memory based system and we are trying to exploit the properties and the capabilities of modern CPUs and their memory architecture to the best that we can. Okay, so no tree shapes is rooted in the observation that implementing tree-based data structures in such systems always lead to some sort of pointer chasing or pointer dereferencing. So let's assume that this do I have space on this slide? I think so, yeah. So that would be one node of our tree-based index structure, assume. Okay, so maybe it's a B+ tree or some variant of that. And of course, because it's a tree-shaped data structure, there would be pointers to subtrees. So let me draw 3 pointers here. All right, okay, drawing with the mouse. All right. Okay, so I'm currently located at this particular node, and of course a search regarding my predicate, my index condition as we've called it, would lead me into this node and then of course further into some of the subtrees. But which of the subtrees will it be? Well, I have to perform some comparisons inside this node. We'll probably compare the literal in the index condition with the separator values stored in this index node, and then I will select one of these subtrees for further exploration. So maybe my wave will lead me here to the right hand side. To access the subtree here on this right hand side, I have to dereference a pointer and access a new portion of memory that holds the nodes in this subtree. This will probably lead to a cache miss, because currently a memory region that holds this particular node is to be found in the data cache. Well, this subtree and its node are probably not found in the data cache, and we couldn't tell beforehand that our next access will probably lead us into this subtree. So prefetching is really tough at this particular point. We didn't know when we enter this node whether our search would lead us into this subtree or this particular subtree. All right, so we will probably suffer from data cache misses on pointer dereferencing on descending deeper into this tree. So in general, tree-shaped data structures are suboptimal in a cache-aware and memory aware DBMS data structure. So we will indeed find index-like data structures inside MonetDB, but they don't come in the shape of trees. So let's delete this. Looks ugly anyway. All right. So, but what do we find? So let's switch on our DBMS X-ray and look at the explain plans again for this simple selection query. We have seen that before, but let's remind ourselves what's actually going on here. Okay, so explain invoked on this particular selection query. So what we will find is a mel program again. All right, and well, we have seen all the components in that mel program. But let me briefly remind you. So we will access the visibility but for the indexed data table. All right, we will then access the A column because the predicate is evaluated on the A column. Okay, so once we've got the A column in hand, we can indeed perform this predicate evaluation and generate a selection vector that indicates which of the rows in the but can qualify regarding this predicate. This is the job of the algebra theta select operation. All right, so this is the predicate evaluation. You will find the literal 42 here. You will find the comparison operation that is being used. You will find all this here. You will even find the application of the visibility information on the A column here. Everything is wrapped into this theta select. And what we get out of this is the selection vector P1. Okay, so that's this line. Well, then we have to construct the result, and the result will consist of the entries in the C and in the B but that hold the C and B column of our index table. But of course, we would apply the selection vector P1 to the C and the B but to restrict the visibility of all those rows that couldn't qualify regarding the predicate. And they would be gone. By this point, the evaluation would be complete, and well, we could construct the two-column view that we use to look at the two-column result at this point, and everything is done. All right, so business as usual, as already known. The algebra theta select with these parameters is used to implement the selection on the A column. Okay. So now let's switch over to a selection on the C column. Maybe something else will happen there, right? So A column is an integer typed column. The C column is a numeric typed column. The A column is a column that could serve as a primary key. The C column could not. I think it carries sign values which will repeat and are not unique. Surely MonetDB will do something about this and exploit that the A column is unique. But let's see. All right, so same query again, but selection on the C column now. We have, of course, adapted the literal here. It's not the integer 42 now, it's the numeric value 0.42, which fits with the domain of the C column. Okay. But, well, when we look at the particular plan that is being generated, so explain on this particular query, we will see the mel program that is generated. You will see that this is just the mel program that we've seen before. Of course, there's no reference to the A column now, and that's fine. But this is just the same structure of mel program. We access the visibility information, we access the raw C column. We will then use algebra theta select to evaluate the predicate on the C column. As you can see, something nifty is going on here. We are using the literal 0.42 in the query, but this has been converted into a short 16-bit integer that just reads 42 here in the algebra theta select. Actually, internally, the C column is treated by MonetDB as being a 16-bit short column. That's something that you can see here. That's a very nifty trick to save the system from doing decimal arithmetic, but instead map all the arithmetic on such a column of type, I think, numeric 3,2 to map the arithmetics and the operations on a column of type numeric 3,2 onto 16-bit short values. Why does this work? Well, this footnote explains this nifty trick that's played by MonetDB. This is the actual type that we had defined for the C column. If you look at the values that this particular type admits, then this would be the set of values that is now admissible. Of course, they have 3 decimal digits, numeric 3. 2 of these digits are behind the comma, so that's the comma 2 here. All right, and well, that's the range of values that you could represent with that. That range of value, the domain, the active domain of the type is really restricted and really small. It holds less than 2000 values. And I can easily represent these 2000 different values using a 16-bit value of type short. All right, so that's rather trivial, rather simple mapping that's going on there that saves the system from doing decimal arithmetic. But this is really sidetracking us. So that's only a few words on that nifty trick that's being played. Otherwise, everything happens as before. We have computed the selection vector. We will apply the selection vector to the C column and to the B column, and that makes up our result. It appears that MonetDB really does the very same thing. Regardless whether our predicate is applied to the A column or the C column, the same thing happens. No exploitation of the fact that the A column is unique. Maybe the A column is even sorted because we have inserted the rows in sorted order so that the smallest A value comes first in the but and the largest A value comes last. Nothing like this. This is reflected in the mal program, it appears. Are these cool characteristics of the columns that are just going unused? And the answer is no, they're not. Okay, of course we hope so. There's something that MonetDB maintains internally automatically, and this is interesting properties that the value distributions in the but tail columns exhibit. All right, so for each but t, there is also something maintained internally that's called prop t, the interesting properties that the tail column of but t possesses. Okay, and that's a whole battery, a whole family of interesting properties that MonetDB maintains internally. I've just listed a few of these here in this table. All right, so there is, for example, the dense property. Okay, so if the but t has the dense property, then we know that the values in its tail column are of type OID. So there are these special offset values that MonetDB can store for us. And we also know that these values are ascending with no gaps. So they are strictly ascending with no gaps. So the values in the tail column could be OID 0, OID 1, OID 2, OID 3. So it's very predictable, the contents of this particular column. Such a column is called a dense column, no gaps. So we could not jump from OID 2 to OID 4, which would still be ascending and sorted, but there would be a gap now. Nothing like that in a dense column. Ascending values, no gaps. We don't have to start with the OID 0. We could start with 39, for example, but then the next value would be 40, 41, 42, and so on. That would be a dense tail column. All right. There's other properties that look less exotic, like the key property. So all tail values are unique in the tail column, no duplicates. So that column could indeed be a key. So unique values in the tail column. The sorter property, well, all the values in the tail column, if I travel the tail column from top to bottom, I will see ascending values. They might not be strictly ascending values, but they are ascending. So there's a sort order on the tail columns, on the tail column established. There's also ref sorted, which would indicate just the reverse sort order, so a descending sort order. All right, and then there's properties like nil and no nil, which indicate that there is maybe one, maybe two, maybe more nil values in a column, or there are no nil values at all in a particular column. All of this can be very helpful information that that can help me to, in these tight loops that MonetDB implements, to have even less checks, because I know beforehand, looking at the properties of the but, that there won't be any nil values present. All right, there's actually a special function, a built-in function, mal function, that we could use in the mal interface that lists all the properties, the current properties that have been inferred for the but t. Okay, Be aware though that this inference, that this derivation of but properties is incomplete. All right. So if, say, the sorted property of a particular column says false, okay, so the tail column of this but is not sorted, all right, then indeed the tail column may in actuality be sorted, but MonetDB didn't have any chance or didn't bother to infer this particular property for us. Of course, if sorted T is true and the property indicates this tail column is sorted, then it will be sorted. But there might be situations where MonetDB misses to derive or to infer a particular property of a tail column, which is a pity because that property could be valuable in query optimization. But, well, the system cannot rely on properties that have not been inferred yet or have not been bothered to be inferred. Okay. Well, this property system is really quite nifty and really advanced. So there's two more things I would like to mention here. There's combinations that make sense of these properties that MonetDB indicates to uses to indicate particular specific situations. For example, consider what's the meaning of a column that has the two properties sorted and ref sorted. Okay, so that would be a column that has ascending, not strictly ascending values, and descending, not strictly descending values. A column that is sorted and ref sorted would be a constant column, obviously. All right, so that would be a column in which each tail value in each row has the same constant value. Okay. Another combination that could be of interest is something like the key and the sorted properties. If both are true for a particular but, then we know that its tail column is indeed strictly ascending. There are no duplicates, but we have ascending values, so that would be a strictly ascending tail column. Okay, so combinations of these properties also make sense, and they're actually being inferred and exploited by the system. Here in the footnote, there is a mention of properties like no key, or no sorted, or no ref sorted, which appear to be the negations of the properties that we've already seen here in the table, but they are indeed a bit more. So these no foo, like no sorted, for example, properties, they are not actually only Boolean properties, but they also come with a proof with a particular row inside the but that destroys the sorted property, for example. So if you ever see, and I think we will see this in the example in a minute, if you ever see a property that has been, the no sorted property that has been assigned the value 3, then this means that at offset 3 in the but, there is indeed a row whose tail value is less than the value just in front of it. So the value for the tail value for row 3 is indeed less than the tail value for row 2, which means, well, the tail column cannot be sorted. And here is the proof. The row at offset 3 is the proof why that sorted property is actually lost. Okay, so it's a really nifty and a really intricate property system that's being implemented inside MonetDB here. Okay, I think it's time to switch over to the terminal again. We haven't seen MonetDB live for a while, so let's do that now. Here we are. And let's inspect this property system for a minute. So let's create a new but, a new integer but, and insert 3 values here. You see they are unique and they are indeed in ascending and strictly ascending order indeed. So let's first do that. All right, and that's what we see. Indeed, it's 1, 2, 3 ascending, strictly ascending order. This could even be a key column. All right, so let's see whether MonetDB has inferred interesting properties about the tail column of this but. So what we will now call is the but info function. and it gives us a display of all the properties that are being maintained internally. And with this IO print, I will just dump all of these properties in the MSQL terminal. All right, lots of stuff here. For example, we can see that the storage for this particular BUT is mallocked, so it's not persistent, it's not in a file, it's just memory allocated. And that's interesting, but not the focus currently. The focus is more on the properties that we've just identified. And well, here you see, indeed, the system has identified that the tail is sorted. So this would be a true indicator. Indeed, the tail is sorted. It is not reverse sorted, so it's not in this descending. It's not in descending order. It's in ascending order. And indeed, the column could serve as the key column, right? No duplicates in that column. That's fine. Indeed, the column also has this property: no ref sorted 1. So now recall that these no foo properties come with a proof that this ref sorted property indeed is not holding currently. And that would be the proof. It's the row at offset 1. Okay. And the row, this is the row at offset 1. It carries the value 2, which is larger than the value in the slot before. And this is a proof that this is not a descending column, right? So this column is, this row is proof that this BUT is not reverse sorted or sorted in descending order. Okay, what else do we find? We find, for example, well, the no nil property. There are indeed no nil values inside the column. Okay, so the T nil 0 here indicates that there is indeed no nil value in the column as expected. Okay. Right, so now let's destroy the strict tail ordering that we had before, and let's see how the property system of MonetDB reacts to that. So I'm inserting 5 and 4 here. This is the BUT and its new state. Well, that's still a column of unique values, but the ascending order has actually been lost here. Okay, so let's see what the property system says about this. All right, still a malloc table. All right. Okay, so you can see that indeed the table is not sorted anymore. And it's also not ref sorted. So it's not in ascending and not in descending order. What's a bit sad is that this key property has been lost. All right, so now that we've performed the insertion, and the actual state of this table says there is indeed still the key property for the tail column. Well, the system has not bothered or has not been able to infer that with the routines that are built in currently. So that's what we are left with. An indication that, well, this should be read as, well, I'm not sure that this is a tail column, a key column, I'm sorry. Please, when you process this column, don't rely on any uniqueness or key properties. Okay, so this no ref sorted is, the proof is still there. Let's see, there is also indication that the sorter property has been destroyed at the row with offset 4. This is the proof that the sorter property does not hold. Okay, at offset 4. This is offset 4 indeed. This row destroys the sorter property because its value is less than the row just before that. So no ascending sequence of values anymore. The property has indeed been lost. Okay, we still have a no nil column, and indeed there is no nils in there. So looks good otherwise. So this property system is conservative and not complete. So we've lost the presence of the key property. So, and you will see that that this goes on like this. If we now delete the row at offset 3 and then look at the state of the table again, then that's what we're left with. We have removed this disturbing value 5 in the tail column and are left with the but that is again in ascending order. It's no nils, as it's unique. It should have all the key properties, the sorted property and the no nil property. And let's look at the result. Well, yeah, that's true. There's indeed no nils in there, or flipped around, nil property is 0 or false. No proof against this. But the system is not able to, or has not bothered to prove that the but is now sorted again. But proving that again would have involved a full scan of the tail column, and the system is not willing, or has decided to not spend this effort on scanning the column and inferring all the properties again. Okay. So we've lost the sorted property in this list of maintained properties, despite it's present in the actual data. And the same is true for the key property. All right. So this is really not a complete inference system for properties, but well, it's still useful to guide the efficient evaluation of operations inside MonetDB. So let's come back to the slides and see how the properties are being exploited and used in MonetDB. Okay, so what happens is that in the mul programs, we saw that one algebra select, or theta select in this particular case, operation. And we were a bit disappointed that particular properties of the A column or the C column have not been taken into account to maybe optimize the internals of algebra select. But that's actually not true. The optimization, the internal optimization of operations like algebra select is based on these properties. And what you see is a sort of, what you'll find in the internals of MonetDB is a sort of decision tree that's being used at runtime, at the time when algebra select has to be performed on the table on the but t. At this point, we will inspect the properties of but t and then look whether it's indeed a dense but. It's the tail column dense. If that is the case, then a selection for this particular literal v here can be implemented very, very efficiently on dense buts. I could follow this path and indeed use direct access. So direct access as a direct offset that will carry the row with value v. I will show you how on the next slide. This is the most efficient method that I can hope for. Well, maybe this but is not sensed, but at least it might be sorted. If this is the case, I could follow this path in the decision tree and at least use binary search on the tail column to guide our search for the value v. All right. If the column is not sorted, then it gets complicated. But maybe there's something that's called an order index on t. All right. This sounds interesting. We will have a look at order indexes in the next video. Okay. So order indexes could be used to temporarily establish a sorted order property on the tail column of the but. And once we've done that, we could then use binary search at least. So that would be the strategy that is indicated by this branch of the decision tree. First, use the order index to temporarily restore a sorted order. And on that ordered column, then we could use binary search. All right. But that, of course, would rely on the presence of such an order index. We will talk about this. If all else fails, then, well, we have to fully scan. We have to do a full scan of the column, of the tail column of but t, to find all the rows in which the value might be v. All right, so that would be the exit strategy here, the least favorable case at the bottom of this decision tree. Indeed, this decision tree is not complete. I've shown here an excerpt of that, an excerpt of those properties that are related to the order properties, the sortedness properties in the tail column, because this is a chapter on ordered indexes. I've not included decisions regarding interesting hash properties, but well, it's just a sketch of the internals of MonetDB. So please be aware of that. All right, so what we've seen here, this optimization at runtime, when this particular algebra select is to be executed, at this point in time, I will look at the properties of BUT-T. This optimization mode in MonetDB is called the tactical optimization. It's performed on demand at runtime, at the very latest, when I know about the properties of BUT-T, or at least all the properties that MonetDB has bothered to infer. Tactical optimization is the counterpart to optimization of a query at query compile time. Or compile the query, optimize it now, have all the decisions made and set in stone, and then start to execute the query. It's different here. This is very late optimization that can react to properties of the BUT-T that have been found to be true when T was constructed, assembled, or assigned. All right, so very nice. This is tactical optimization. So let's see what these tactical optimizations of algebra select, what they entail. So for example, if algebra select detects that its argument but is indeed a dense argument but. Well, a dense argument but indicates that the tail column is carrying OID values. I think this but here, this should be a dense but. All right, so let's look at the tail column. It's indeed a column carrying OID values, so check for that. It's indeed a column in which all the values are strictly ascending from 39 here up to 44. That's a strictly ascending order. All right, and there are no gaps. We are starting with 39 here and then 40, 41 and so on. There are no gaps until we reach the 44 below here. So it's a column of OID values that's strictly ascending and has no gaps. This is a dense but. In this particular case, there's the obvious, very obvious way to implement the algebra select operation of this kind. We are looking for all rows that carry the value 42. Well, we know that this is a strictly ascending but, so there can only be one match inside this but. If there is any match at all, there will be only one match. And how will we find that match? Well, we'll simply look at the first entry here, at the so-called seg base of the column of the but column here, which is 39. Well, we know where to find 42, but it's just the difference between 42 and 39, the seg base here, which would yield an offset of 3. At offset 3, there must be the matching row. All right, so we can convert a value-based access. We can convert the value-based access into a positional access, into an offset-based access, which is the best mode that we can hope for. All right, so that would be the algebra select for one literal on a dense but. Of course, this is the preferred mode of evaluation. There's other versions of algebra select that are looking for values in a range of literals. So we are looking for all rows that are in the range between 40 and 42 inclusive. That's the two true values here. And we are indeed looking for the values inside the range, not outside the range. This is indicated by this false value. All right, but this is our target range. All right, so if we know that the argument BUT-T is indeed dense, we can use such offset calculations to find the minimum and the maximum offset of inside the but that will carry all the matches for this particular range. And we could then just use a so-called algebra slice operation, a non-destructive operation on this but that will just give us a view of this input but, a view that only includes the rows that are inside this indicated box here, a view of the original but that will contain just the matches. This is also a very cheap operation. We don't have to copy data there. We would just respond with a view of the input BUT-T that contains the rows in the window. And again, the border of the window could be just computed by simple offset or subtraction operations. The best case we can hope for. All right, that would be one tactic that is implemented by algebra select in the presence of dense butts. If the butt is not dense, but if it's sorted, well, then we could at least maybe do something better than a full scan. We could, for example, use a binary search here. Okay, binary search for the value 42 in the tail column. You see that this is indeed a sorted column. It's indeed a unique column, but that's not, or a key column, it's not of importance here. This is a sorted column, so we could just use binary search. Looking for the 42, we would just compute the pivot element, the element to compare with in the middle between the low and high element that we find in this particular column. That would be just the 41 here. We would compare the 41 with the value that we are searching for. 41 is less. So since the column is sorted, the value that we're looking for must be in this range below here. And that's what we would do. We would find a new pivot, the middle element in this new range, and that would be just the value 43 here. We would compare with our search value 42 and find that 43 is larger. So the result must be found in this particular subrange. This would be the new pivot. We would compare with our 42 value and indeed find it. That will take, of course, a logarithmic number of steps in the size of the butt. All right. This is indeed better than just a full scan. It's, it involves less comparisons and less steps in the overall algorithm, but of course it involves the comparisons of our pivots with the search for values. So these comparisons indicated on the slide here. And the outcome of these comparisons is completely unknown. So sometimes the search will lead us into the upper or into the lower half of the still active range of the butt, and we cannot tell beforehand which half it will be. So these jumps are hard to predict. They will lead us into regions of the butt. They may not be in data cache already if the butt is large. So that is really, that's a cool strategy, but it's less than ideal in the presence of modern CPU architecture and the caches and branch prediction that we've talked about. Okay. So much for that. There is still the tactic of algebra select that is building on order indexes, if you recall the decision tree of the previous slide. But let's not talk about this now. Let's talk about order indexes in the next video, because I think they deserve a little more time. Okay, I hope you will be around when we talk about order indexes. See you then.